Go into the next topic with respective to the second module, which is pertaining with scaling and small geometry effects and along with MOSFET capacitances. So the purpose of this particular topic is we need to shrink the size of the IC. When you're shrinking the size, you have to have a different dimension. So the dimension exists as it is, but you have to scale it. You have to have a parameter which has to be scaled. Normally we write the scale on the graph. So 1 centimeter is equal to 10 volts or 1 centimeter is equal to 1 meter. But that doesn't represent that it is 1 meter. Then when you go back and scale up, you do the reverse procedure. If you have 5 blocks on your graph, it is nothing but 5 meters, because one block represents 1 meter. So this is how the scaling helps us, and we are all quite familiar by now, I hope. So we'll look into this topic now. The design of high density chips in MOS VLSI is high, so the sizes of the transistors are as small as possible. Now we are talking about VLSI. What is VLSI? 10 to the power of 7 to 10 to the power of 8 components are fabricated on an IC. So you have more and more number of ICs or transistors or devices being placed on the board base. Therefore, this is called as VLSI, and this in turn is also called as density. It is highly packed. So the number of components being placed is high, and in order to accommodate more density, you have to have smaller sizes. So thin people can sit 5 in a row, whereas stout people can sit only 3 in a row. So that is the advantage of being thin or being small. So the reduction of the size, that is the dimension of the MOSFETs, is commonly referred to as scaling. As I already told you, the operational characteristics of a MOS transistor will change with the reduction of its dimension and their physical limitations. So when you scale, definitely the operation characteristics will definitely change of the MOS transistor. It behaves in a different way, and there is always a because of the reason that it is reduced in dimension, and there are some physical limitations as well. The smaller sizes definitely have some limitations. And in order to understand the scaling, there are two types. One is the full scaling, which is also called as constant field scaling and constant voltage scaling. So these are the two types: constant field scaling and constant voltage scaling. So we will examine the scaling strategies and their effects, and we'll consider physical limitations and small geometry effects. As I already told you, this is the essence of our topic. We will go to understand about all these things. So scaling is nothing but reduction of overall dimensions of devices, preserving the geometric ratios. So what do you mean by geometric ratio? You know, the area of a triangle is L into W. So L and W should remain as it is, except that you have to shrink down the size. So reduction of the overall dimension. L is equal to 1 centimeter earlier. Now L may not be equal to 1 centimeter, it is 0.5 centimeters, but still L remains as L itself. So scaling would result in reduction of total silicon area, thereby increasing the overall functional density of the chip. As a result, the reduction area of one particular IC is reduced, and as a whole the density is increased. So we have a scaling factor which is indicated or denoted as S. So the constant scaling factor S is greater than 1 has to be considered. So S value should be greater than 1. Now what is S and how are the relationship associated with S is what we need to understand. These are the three types of scaling, called as full scaling, which is also called as constant electric field. So in this, the electric field is going to remain constant and all of the parameters are going to change. So the dimensions and the voltage scale together are scaled by the same factor. Fixed voltage scaling, so voltages remain constant and most dimensions are going to get scaled. And the next one is a general scaling, which is very much in general, which is with respect to the voltages and the dimensions. So this is the scaling of a typical MOSFET by a scaling factor S. So as if you look into this, I hope you can gauge this is the fabrication cross section. You have the substrate, you have the channel, you have the N diffusion or P diffusion, depending. Okay, doping is Na, so it is N type. We are not sure. So doping depending on what type of doping is there, you will have the right type of diffusion. And this is the channel. This is the front view we are familiar with. In between the channel, you notice there is an oxide. Above the oxide, you have the gate. Right? Please try to visualize this diagram. And from the diffusion, you pull out the lead, that becomes your source. From the another diffusion, you pull out the lead, that becomes your drain. And as a whole, the entire chip is identified here with respective to the channel size. So the channel size is L, and the channel width, you see, this is the whole thing. So this becomes the width of the channel, and this becomes the drain. So oxide has a thickness, thickness of oxide is given as Tox. This is the thickness of oxide, and this is a new dimension, length, width, height of the channel or height of the diffusion, which is indicated as Xj. So I hope I am clear with this information. Now how do we associate it with scaling? So whenever you are talking about doping, doping is normally indicated as Na, ionic concentration of the doping. This has to be multiplied by S. So the doping, these are the few things you have to remember. There is no choice. Please make a note of each and every statement I am talking. So the doping, Na, is the doping representation, concentration of the ion or impurities. This has to be multiplied by S. Next you have the length, L dash. So new length is got by, if the original length has to be scaled by S, L by S, whereas doping is N into S. Next you have diffusion doping. Diffusion doping, when you have the substrate doping as into S, similarly the diffusion doping is also into S. If L is equal to L by S, obviously the dimensions are also reduced by scaling. It's nothing but divided by S. So L is equal to L by S, W is equal to W by S, Tox is equal to Tox by S. So the dimensions are also scaled by S. Next, height. Height is also a dimension. So height of the channel is also scaled by Xj by S. So this has to be remembered. I have given 1, 2, 3, 4, 5, 6, 7. 7 parameters. So only in that 7 parameters, dimensions are always divided by S. Apart from the dimensions, voltage or any other doping or any other informations will be multiplied by S. Now we find out the difference between constant field scaling and constant voltage scaling. So priorly we are considering the constant field scaling. This attempts to preserve the magnitude of internal electric fields in the MOSFET while the dimensions are scaled down by a factor of S. So always in constant field scaling, the dimensions are scaled down by S. So S is what we normally take, and the purpose of S is to retain the intensity of the electric field, whatever or magnitude of the electric field. So the dimensions are only scaled by S. Rest all are multiplied by S. So L is a dimension, W is a dimension, Tox is a dimension, height or junction depth is also a dimension which is divided by S. And power supply is also divided by S, threshold voltage is also divided by X. Yes. So all this, the dimensions are scaled down by a factor S. And list the significance factors, potentials, doping densities are multiplied. Just now what we had a discussion, it has been given here as a tabular column. Next we have a parameter called as gate oxide. So right now we are familiar with this term gate oxide, which is below the gate layer, and normally it is thin ox. So the gate oxide capacitance is the capacitance which is existing between the gate oxide or within the gate oxide per unit area is given by this formula. So we know C, capacitance is equal to epsilon by D. So epsilon is the permittivity, D is the spacing between two parallel plates. But here we are considering the capacitance of an oxide. So it is given as Cox. And when we are talking in terms of parameters called as scaling, the scaling parameter associated with the original capacitance will give you another value which is called as Cox dash or Cx complement. So since it is oxide, we have it as epsilon Ox divided by Tox dash. So when you have epsilon and Tox dash is Tox divided by S. So the remainder, the denominator S will come to the numerator, Therefore, you have an expression as S dot epsilon OX divided by T ox. In other words, epsilon OX and T ox is nothing but C ox. So, C ox dash is equal to S into C ox. This is one important formula you need to remember, along with the original previous dimensions which I have already told you. Next, we need to consider the aspect ratio. So, we know what is the aspect ratio, W by L. It will remain unchanged under scaling. Next, we have transconductance, which is indicated as Kn. This also will be scaled by a factor of S. Terminal voltages are also scaled down by a factor of S. Voltage, terminal voltage, that is VDD and VSS. And as a whole, now we come back to the important expression, which is the linear current expression. So after scaling, you have it as ID dash. So use the transconductance parameter. As I told you, transconductance is scaled by factor S. So Kn dash is nothing but S into Kn. It is scaled by a factor of S. Kn dash is nothing but S into Kn. 2 constant, it remains as it is. Next, voltages. They are also scaled down by S. Scaled down means you have to divide. Scaled by means you have to multiply. So VGS dash is nothing but VGS by S. VT dash is VT by S. So when you take this, the LCM, S is remaining as a common factor and you pull it out, it becomes S. Next, VDS is nothing but VDS by S. VDS again VDS by S. So when you scale out, when you do the LCM and you simplify the expression, you have S into S square. So if you just consider 1 by S square and S, it is nothing but 1 by S, and originally IDS expression is Kn by 2 into 2 VGS. So you have the expression as the IDS, the linear current equation is scaled down by S. So this is how the scaling parameter with respective to the drain current is found out, and transconductors is scaled by a factor of S, so it is multiplied, and voltages are scaled by a factor of, scaled down by a factor of S. Same thing with voltage, threshold voltage, same thing with the drain voltage, and appropriately the respective voltages are substituted. And yeah, 2 is not here, so this is not there, sorry. 2 is retained inside itself. Once you do this, you will be getting back Kn by S into IDS. So the current is scaled by a factor of S. The same occurs with respect to saturation current. Here also, when you appropriately substitute the values, for example, you know this, the transconductance is replaced by S into Kn divided by 2, and VGS is VGS by S minus VT by S whole square. So when you take the LCM, S square comes and that is removed outside. Therefore, S and S gets cancelled and you are left out with Kn by 2 into 1 by S VGS minus VT whole square, and you substitute, that has to be found that it is nothing but the saturation current divided by S. So linear current and saturation current is also scaled by a factor of S. Now we will find out what is the equivalent scaling factor for power in full scaling. So here the drain current and the drain voltage are reduced by a factor of S. We are already aware of it. Just now we saw what is the current, which is ID dash is given by ID by S. And similarly VDS dash is given by VDS by S. So P dash is ID into VDA, which is ID dash and VDS, and when you substitute, both comes as S and S, and it turns out to be ID VDS by S square. ID VDS is nothing but P. Therefore, P dash is equal to P by S square. So that is how the power is scaled by S factor, S square. Next is power density. Then power density is power by area. So we already found out what is area, or we have, if not, you can have a note of this. You can have a note. Area is equal to L into W. So L and W are scaled by 1 by S. Therefore, this is equal to 1 by S square. Area is scaled by 1 by S square and power is scaled by 1 by S square. So it retains the same. Area is equal to so much and P we have found out as P by S square. So P by S square into 1 by S square will be divided by will be into S square. S square gets cancelled. It remains as P itself. So it is ultimately remaining as the same parameter P by area. So when we look into this, all the while we were looking about constant field scaling. Now we look about the constant voltage scaling. So certain voltage levels for all input and output voltage would necessitate multiple power supplies and level shifters. So in constant voltage scaling, all dimensions are reduced by a factor of S. So we will see how it goes on. Now we will check about constant voltage scaling. So voltage is not going to get scaled because the voltage remains the same. So ID dash linear is given by Kn by S, Kn dash into 2 into VGS dash minus VT dash into VD dash S dash minus VDS dash whole square. So substitute Kn, we know it is S into Kn by 2, 2 into VGS minus VT into VDS minus VDS whole square, because it is remaining the same, no changes except for Kn dash. And finally you check S, if you take out, it is Kn by 2 into 2 into VGS. So it is, this whole thing is nothing but your linear current expression. So it happens to be that ID dash in constant voltage scaling is S into ID, especially in linear region. So the linear current is S into ID. Similarly, Cox, it is increased by a factor of S, therefore that is also used for scaling, and we'll see go on seeing about in the next slides. So these are the constant voltage scaling of MOSFET dimensions, potentials and doping densities. So if you have the dimensions in constant voltage, it is reduced by S. So W becomes W by S, L becomes L by S, Tox by S, Xj junction depth is Xj by S. So everywhere it is reduced by S. Voltages remain unchanged, VDD and VT. Doping densities, earlier it was Na into S, but here it is Na into S square. It is increased by S square. So these are the parameters which has to be remembered in terms of constant voltage scaling, and we'll see how exactly the saturation current exists. So the saturation current is given by Kn dash by 2 into VGS minus VT dash whole square. So these are not going to change, they are remain the same, and transconductance becomes S into S. So that is only parameter which has been changed here. And if you look into it, it is nothing but this whole thing is your ID, therefore it is S into ID sat. So linear current as well as the drain saturation current is scaled by a parameter, scaled by a factor of S. It is multiplied, it is increased. So that is what we wanted to show you in this difference between constant field and constant voltage scaling. Similarly, power dissipation, P is equal to I into V. So I is scaled by into S. Just now we have seen VDS remains same. So S into ID into VDS is S into P. So power is also scaled by multiplied by S. It is enhanced. It is not divided. So oxide capacitance Cox. Cox is also scaled by S. Drain current is also scaled by S. Power dissipation is also scaled by S. Whereas power density is P by area. So area is scaled by S square. P already is multiplied by S. So when you bring it back, it becomes S cube. So power density is scaled by a parameter of S cube. So these are the appropriate questions appearing in the VTU question paper. Explain the constant field, constant voltage scaling models with a diagram and scaling effect table. So the diagram and the tables will represent the answer for this question, which can fetch you 6 marks. Derive the scaling parameter for the device parameter, parasitic capacitance, channel resistance and gate delay. Already I have shown you You can just refer back to your notes. Next, define scaling. Explain the scaling factors for device parameters. Same thing. So yeah, the same questions repeats again and again. What is the parameter for gate capacitance, gate area, saturation current, saturation channel resistance, operating frequency? Each one of them, 8 are there. Each may be fetching you 1 marks. Separately 6 marks. So almost it is equivalent to 1.5. 1.5 marks for each of these answers. So if you refer back, you can get an idea about all these things which has been discussed.